there are other techniques called as, let's say, Hartley technique, where you don't want to design an image rejection filter because there's insertion loss in the filter. You're having an amplifier, then you want to immediately filter. This image reject filter should not have any reflection loss that goes back to the amplifier, is also no good. So to circumvent all those problems, is there a way that you don't want to have an image reject filter? You can, where you're doing kind of a IQ. You're splitting the RF into a sine and a cosine, into a sine and a cosine product. It's just that when you multiply by the sine and the cosine, you make sure that when you do the multiplication and addition to recover back the IF signal, the image frequencies add up destructively and the RF frequencies add up constructively, so that naturally the image gets rejected and RF passes through. How to do that? The block diagram is here. You have the local oscillator. This guy creates the LO. If you feed directly, that is the sine omega t. If you shift it by 90 degrees, you know that sine curve, if I shift it by 90 degrees, it's cosine omega t. So you can imagine this to be my in phase, and this is the quadrature phase. And when you multiply it and low pass filter it, you don't combine the I and the Q directly, but you phase shift the Q by 90 degree. You phase shift the Q by 90 degree. That's the extra thing that you need to do, but you're doing it at a lower frequency of IF, because after the mixer, what you get is already IF, intermediate frequency. You're not having this filter, but instead you're using this phase shifter here. So there is an asymmetry in the system with 90 degree there, but nothing over here. How does that work? You can go ahead and see the math here at the different points 1, 2, and 3. The voltage at 1 is going to be omega RF minus omega LO and omega LO minus omega image when you multiply it, where I'm having a sine omega RF t coming in here. Sine omega RF t times sine omega LO will give me this. Sine omega t times cosine omega LO will give me this. If I go ahead and shift it by 90 degrees, I would end up the sine becoming cosine, but the image will become negative, whereas the RF will become positive. So when I go ahead and add W2 and W3 to get V4, the RF gets added constructively, the image gets added destructively. It's a nice concept. Yeah, mathematically it works. So when I add this up, this term and this term cancel each other. The image is gone. So you don't even have to have an image filter, but you need to realize this 90 degree phase shift. So since there is an asymmetry of 90 degree phase shifter here and not there, so there was a variant to it, which is called as the Weaver technique, where you're having a kind of symmetry between both the phases, but additionally you're doing it in two parts. Yeah, you are doing what is called as quadrature mixing as well. That means after you do a down conversion, you are subsequently mixing it with a second local oscillator here before obtaining your IF. The newer trends that you see in RF is to go for zero IF altogether. That means previously we saw here that once I have a omega IF, you see that image is going to be 2 omega LO minus omega RF. 2 omega LO, 2 omega LO minus omega RF. That's my image frequency. But if I were to have no local oscillator at all, what if that means my local oscillator is same as RF. That means omega LO is equal to RF. This becomes 2 omega RF minus RF, so it is omega RF. So my image frequency is exactly RF. That means my intermediate frequency is 0 if I have no intermediate frequency. That's called as a zero IF receiver. You don't even have to worry about image filter there. So again, you can have in phase and quadrature phase representation. And more importantly, these days, what you're seeing is digital IF receiver, where once you have this IF frequency, you are having an analog to digital conversion Instead of converting to baseband after IF, you're directly going to the digital domain using an ADC, analog to digital conversion. So you're doing digital demodulation. You're doing a digital demodulation rather than using analog from IF. So that's a digital receiver. A fully digital receiver, that's a digital IF receiver. A fully digital receiver is you don't even go for IF. You directly sample it at RF. This is sampled directly at RF. So you don't even have a IF stage altogether, an intermediate frequency stage altogether.